Alright, so we've had a lot of questions about epoxides and kind of how they're formed. So let's just draw one out here for us. Let's see an H there. This came from this alkene. The question is going to be, how does this alkene react with this peroxy acid? So like that. So the way it does that is actually very similar to how it reacts in HBr, if your oxygen. Right, and of course this is flat, so we could also have the enantiomer of this. And the way it works is the pi bond attacks the oxygen, very similar to Br2. That makes these electrons go here. Those electrons go there. These electrons come back down. So it's kind of like this swirl of electrons. It starts here, breaks the oxygen-oxygen bond, pi bond breaks, those electrons go there. Because the byproduct of this is actually this, carboxylic acid. Right, so that's kind of how the process works. There's 1, 2, 3, 4 arrows. It all happens at once. Alright, so if I were to mark this up, that's the blue oxygen. That blue oxygen's there. If I were to mark the red oxygen, that's that one right there. That's where that ends up. Right, and then I guess if I had the black oxygen, that's the one that ends up as the carbonyl now there. So a pretty complicated mechanism. 4 arrows, all kind of flowing back down around. Right, so in the Br2, right, similar to Br2, because in the Br2, right, our pi bond attacks, the Br bond breaks, and then these lone pairs come down. So it's somewhat similar to the Br2 mechanism as well. You gotta remember, it needs that extra bond to come back down to make that another CO bond. That's the key. So another good question is asking us about these Markovnikov and anti-Markovnikov products. So let's just take a look at a potential alkene, something like this. And what we want are both the Markovnikov product, right, where the OH is on the more substituted carbon. So we would have added an H. So this is that Mark product. We also want to be able to get the anti-Markovnikov product, the anti-Mark product, right? The anti-Mark product where the OH would be here. So let's do a couple things first. Let's number of carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's draw on our H's on our pi bonds. Alright, good. So maybe there's an H there. There was always an H there. Good. Don't need to worry about lone pairs. Add lone pairs in. We could do bonds, broken bonds form, but we're not going to do that, just for ease of time. If I want to get something on the more substituted carbon, there's a way to do that. And those reagents are H plus, or H2SO4, in water. That would give me the Markovnikov product. If I want to get the anti-Markovnikov product, I don't use those same reagents. I use a different set of reagents. Those reagents are, first step would be BH3. The second step would be that OH minus, right, that switch out. That's a different mechanism altogether, and actually adds the OH onto the less substituted carbon. Because boron, when it adds, wants to be in less substituted carbon. And boron ends up switching with OH. Excellent. So let's go through the whole mechanism for all of these. Now I'm going to shrink this guy down. So if we go to our first one, draw on our H, 1, 2, 3, 4, 5, 6. We're going to react it with H plus in water. First step, pi bond attacks, that's our nucleophile. Attacks H plus is my electrophile. Since I'm going to form a carbocation here, I want to form the most stable carbocation possible, so I added the H to carbon 3. 2, 3, 4, 5, 6. It means I need to get a plus charge on 4. Balance my charge always. Now at this point, if I could do a rearrangement, I would, but it's a tertiary carbocation, so it seems pretty good. I'm going to have water attack, because there's lots of water around. It's a solvent, it's below the arrow. It attacks. The lone pair of the oxygen is a nucleophile. Attacks the carbocation. One thing people will mess up here, you need to make sure you balance your charge. So the oxygen does have a plus charge here. Right? The oxygen didn't lost electrons. You can't do more. Don't try to do too much in one step. So 1, 2, 3, 4, 5, 6. The last step is actually just regenerating our H+, which is actually a catalyst and would be indicated as such. So that would be just these electrons going back to the oxygen to give us the product. The OH. And to balance our charge, H+ was formed. We start with the plus charge and end with the plus charge. Also start with the catalyst. Need to make sure we regenerate the catalyst. Number our carbons, 1, 2, 3, 4, 5, 6. Good to go. Markovnikov product. Right, the group added Markovnikov product added to the more substituted carbon of the pi bond. That's Markovnikov. So H+ and water will get that done. Stereochemistry doesn't matter here, right? If we go through a carbocation, of course we could add from the top or the bottom. So don't worry about the wedges and hatches. Also, we didn't make an asymmetric center here. So there's not a stereoselective reaction. It's a regioselective reaction. We picked one region over the other, but it's not stereoselective. So let's shrink this up. Let's take that same thing. Number of carbons, 1, 2, 3, 4, 5, 6. John or H. Let's look at how it's going to react with BH3, which of course has an empty p orbital. Right? Doesn't have a flow octet. So in this case, what actually happens, actually I'm going to erase my BH3 and draw it a little differently because I know I want the boron to go on the left substituted carbon, I want the H to go on 4. So I'm going to draw it like this. So it's kind of lined up a little better. Right, so here what happens, pi bond attacks, that's always nucleophile, the empty p orbital, and at the same time this H comes in, right, and attacks. So I would draw this very similar to the bromonium ion. I'd say, well, this H here and that methyl there on the same side, the ethyl and the methyl on the same side, and here the boron and the H we just added, these other two H's are syn, right? This is that syn or cis addition, right? The second step would just be OH minus, right? That's step 2. This is step 1. Step 2, all we do is replace, well, renumber our carbons, 1, 2, 3, 4, 5, 6. So the boron and the H on the same side, so the OH and the H will be on the same side as well. So H, ethyl, and plus you'd also have its enantiomer. So this reaction is also regioselective because it's selecting for carbon 3, right? 1, 2, 3, 4, 5, 6. It's also stereoselective because it always has a syn or cis addition. So you make both enantiomers here. Right? The OH could either add, the boron could add it from the top as well. So you make both enantiomers as well. Very good. So if we're thinking about intermediates for these, let's pull this one back down. Move that out of the way. Let's pull this guy back up. Let's draw a free energy diagram for it. So we'd have the starting material. We have the intermediate A, intermediate B, and then our product. So our free energy diagram, energy, reaction coordinate, we'd have our starting material. Our intermediate A is a carbocation, so it's going to be higher than our intermediate B, which is, there's a plus charge, but it has full octets at least. There's our product. First step is going to be really slow because that's forming a carbocation, high transition state. Next one's going to be fast, even faster yet. So we have 3 transition states and 2 intermediates, right? Every arrow we have counts as a transition state, and we have 2 intermediates. So that's what our free energy diagram would look like for this. So let's take that now. See if we can't shrink that guy down. What would it look like for the boron? Now for the boron one, let's go ahead and label these. So we'd have starting materials, or intermediate A, and then intermediate, oh, this is product, excuse me. This would actually be our final product. So for this one, our free energy diagram would look like energy, our starting material. I don't think our product's too high in energy. It's not super stable, because boron's still, again, right? Boron's still here, again, doesn't have a full octet. So it's probably maybe here. And that breaks down pretty fast to go there. So the slow step is the first step, probably. Couple transition states. Right, we have 2 arrows, 2 transition states, 1 intermediate. Good to go. Let's maybe work on some definitions here. Talk about what is chiral. A chiral is a chiral molecule. It's something that has a non-superimposable bad spelling. Try again. Non-superimposable mirror image. And an achiral molecule does. Some examples, right? Non-superimposable chiral molecules usually have asymmetric centers. Of course, what's an asymmetric center? Right, chiral molecules, except for meso compounds, have asymmetric centers. An asymmetric center is an sp3 hybridized element. Right, sp3 hybridized, and it has to have 4 different things bonded to it. Right, so most chiral molecules have asymmetric centers, except for meso compounds, which we'll get to in a second. So let's talk isomers. So we shrunk that down. Let's talk some isomers. Easiest ones to remember are constitutional. Right, constitutional isomers have the same molecular formula, but different bonding patterns. So a great example is this. Right, these are 2 constitutional isomers. They have different bonds or different bonding. Same molecular formula, right? But different chemical and physical properties. For sure. Those are constitutional isomers, right? So bigger. So another type of isomer is, so I'll kind of put the constitutionals up there. Another one we've learned about is cis-trans isomers, right, or EZ. Again, right, we know that this is the E isomer, or the trans, this is the Z isomer. And we've talked about how to decide that by breaking it down the middle and ranking. So these are cis-trans isomers. They are asymmetric centers. Right? This carbon and both these carbons of the alkene are actually asymmetric centers. No, excuse me, not asymmetric centers, they're stereo centers. So these are stereo centers. Right, stereo centers. To be sure, there's stereo centers there. And so are these 2 carbons. Cis-trans isomers have, again, different chemical and physical properties. And the trans, or the E, or trans, is always more stable. Most times more stable. Good. Another type of isomer is an enantiomer. Right? Enantiomers are usually chiral molecules. Right? So in this case, you'd have something that has a mirror image. So if I said A, B, D, and C, this would be A, B, D, and C. See how there's a mirror plane there? So these are enantiomers. It's like our hands are enantiomers. So it has actually the same physical properties and chemical properties. Except with plain polarized light, and in cases where they interact with other chiral molecules. Right? With other chiral molecules. Right? They're actually different. They'll interact differently. So that's when they will. Normally, they have the same chemical and physical properties, except when they're interacting with other chiral molecules. Right? Think about shaking hands. Right? Two right hands can shake. Two left hands. A right and a left can't, because your hands are chiral. So think about the handshake idea. Again, these are chiral because they have a non-superimposable mirror image. Right? sp3 hybridized with 4 different things. These are asymmetric centers. Right? The carbons here are both asymmetric centers. They're also stereo centers. Very good. So diastereomers. Right, you need to have more than one asymmetric center in that case, and they have different chemical and physical properties, so one must stay the same. At least that basically means that at least one stereocenter is different. At least one is different. More than one can be different. Those are diastereomers, so at least one is different. But you need to have 2, hence the 2. Quick examples of diastereomers. Right, if you do a compound, you have it has 3 stereocenters. Say it's R, R, S. A diastereomer would be S, R, S, right? There's one different, right? One stereocenter is different. So it has a different, right? These one stereocenter, these are 2 are the same, but these one's different. So they have different chemical and physical properties. Those are diastereomers. Good. Let's scrunch that down. Now let's talk about meso compounds. Meso compounds are compounds with, it has asymmetric centers, but it is achiral. Right, and that's very unusual because most times if you have asymmetric centers, you are chiral. So the reason it's achiral is because there's an internal mirror plane. So it has a superimposable mirror image. A lot of times you'll see this with rings, or you'll see things, right? There's 2 PRs here. Right? Each of these carbons is bonded to 4 different things. So it's 2 asymmetric centers. But there's an internal mirror plane, right? You can see a mirror there. So this compound is meso. So it has asymmetric centers, but it is meso. It's always talking about one compound, whereas in the enantiomers and diastereomers are talking about comparing 2 different things, right? We're comparing 2 compounds here, 2 compounds here. This is just referring to one compound with a mirror image. So it has asymmetric centers, but it's achiral because it has that mirror image within the thing. One way to think about it is that we are meso compounds. We have asymmetric centers, like our hands and our feet are asymmetric centers, but we have a middle mirror plane through us. So we are actually meso compounds. I'll do some quick naming practice. Let's see. All right, something like this. Let's make sure we number our carbons correctly. The longest parent chain, including both pi bonds. So I'd go 1, 2, 3, 4, 5, 6, 7. So that'd be my longest chain. So that's going to be a hepta, because there's 2. It'd be a heptadiene, because there's 2 alkenes, diene. I know to tell you where people need to tell people where the alkenes are at. It's at carbon 2 and 4, so it's a 2,4 heptadiene. I need to say what else is off this. There's off carbon 5 and 4, so I would say 4, 4,5-dimethyl. And then the final piece, which I need to add, is whether these are E or Z alkenes. So in this case, the carbon at 2, I would say, is a 2E. This is all out in front now. Oops, don't want to put a parentheses there yet. Comma. And the one at between 4 and 5, that is actually a 4Z alkene. That goes out in front. So make sure you don't forget the E and Z part as well. Another example, throw up a 5-member ring here with a Cl on it. Parent chain is going to be in the, it's going to actually be in the ring. So if I want to number the ring such that I get the substituent lowest possible, so I would go 1, 2, 3, 4, 5. So that's a cyclopentene for my parent chain. Cyclopentene with an E. I have a 3-ethyl and a 4-chloro as well. So 4-chloro, 3-ethyl, cyclopentene. Good. Let's quickly rehash some mechanisms. So if I were to take that same pi bond as from before and have it react with Br2, what would that look like? So let's number these carbons, 1, 2, 3, 4, 5, 6. Drawing all our lone pairs. And draw the H's on any reacting alkanes. First step, pi bond attacks the bromine. Carbon-bromine bond breaks. When electrons come back from bromine to clamp down, that forms a bromonium ion. I'm just going to draw one enantiomer of it. I'm going to use this. That's the way I like to draw it, since it's not in a ring. I like to use the wedges and hatches. Because I know that the ethyl and carbon 2 and 5 are on the same side. So if I go 1, 2, 3, 4, 5, 6, notice how they're both cis to each other in the alkene. They'd be cis, so they're both hatched. I'm going to put the bromine, just draw one enantiomer of this there. Draw in the lone pairs. Make sure I balance my charge. So there's Br minus floating around. But in this case, let's say I add in another element. We're in ethanol as a solvent, so there's a lot of ethanol floating around. So now ethanol is going to be my nucleophile in the second step. Draw in its lone pairs. Which carbon to attack? I'm going to attack carbon 4, because that's more substituted. It's going to have more stable delta plus stabilization. It has to be trans, because that's where sigma star is at. Kick up. I don't need to change the wedges and hatches. I just fill that in. Right. Notice how the H and the carbons are still on the oxygen. They never left. I got to balance my charge. Bromine got more electrons. That's of course an R there. And there's still one there. So my plus charge now is on my oxygen. There's still a Br minus floating around. And that's going to take that last H. And that's going to show, I will have the bromine and the oxygen as part of the ether now. On opposite sides, and I also made HBr. I also made the enantiomer of this. So how would I draw that? So I was going to draw the enantiomer of this. I would simply say, let me number my carbons again. Sorry, I got away from that. 1, 2, 3, 4, 5, 6. I wouldn't change anything except there's an H. I would put the bromine down here on the opposite side and have the alcohol here. So I didn't change where the alcohol, or the alcohol attacked. I just changed whether it was on the bottom or on the top. All right, so I just flipped it around. This is the enantiomer of that product. Good. A couple of ozonolysis problems. We take that alkene here. We treat it with O3. We number our carbons. 1, 2, 3, 4, 5, 6, 7. We'd split her down the middle there. We would see a new aldehyde. And we could draw the H in there. We'd also see a new ketone. Numbering our carbons, make sure we didn't lose any. 1, 2, 3, 4, 5, 6, 7. Good to go. Another example could be in a ring. Again, numbering our carbons. 1, 2, 3, 4, 5, 6. We're going to react it with ozone. Just split it there. Split it there. So we form, there's H's here. We're going to form some aldehydes in this case. Number of carbons, make sure we didn't lose any carbons. Never lose a carbon. 1, 2, 3, 4, 5, 6. Good to go. Done. Alright, finally talking about what we do here if we have H2SO4 and we have perhaps methanol floating around. What's that going to get us for a product? Hey, maybe think about free energy diagram. So H2SO4, I would just redraw as H+. Right, drawing all our lone pairs. Draw the lone pairs in on the methanol. Below the arrow, that means it's a solvent. Right, below the arrow, it's a solvent. Number our carbon. 2, 3, 4, 5, 6, 7. First step, pi bond attacks, H+. Pi bond's a nucleophile, H+ electrophile. We form a carbocation. We want to form a carbocation in the most substituted carbon because that's what has the most hyperconjugation stabilization. And that in this case would be 1. Number our carbons. Oh, could draw an H in here. So carbon 2 got another H bonded to it. So 1, 2, 3, 4, 5, 6, 7. Carbocation means we can attack from either the top or the bottom. Right? It's sp2 hybridized. So in this second step, alcohol is going to attack. It does that. It can attack from either the top or the bottom. So it'd be West or hash, but it's not going to matter in this case. H is still bonded to that oxygen. So balance our charge. The plus charge is now on the oxygen. Number of carbons. 1, 2, 3, 4, 5, 6, 7. And to balance our charge back up, we need to regenerate. The H2SO4 is actually a catalyst. So let's regenerate that. Give those electrons back to oxygen. So our final product would be an ether. So 1, 2, 3, 4, 5, 6, 7. And then balance our charge. We start with H+, we finish with H+, because it's a catalyst. So that's how we know we're done. What would this look like in a free energy diagram? Let's label everything. Starting material. Intermediate A. Intermediate B. And the product. So energy. Start material and product. I'm not really sure if one of them is more stable than the other. But I do know intermediate B, or intermediate A is way high in energy, because that's the carbocation. And intermediate B is probably not too bad. So it's way up here, here. First step is going to be the slow step. That's forming a carbocation. All the other last 2 steps are going to be fast. So we have 1, 2, 3 arrows. So we should have 1, 2, 3 transition states. We have 2 intermediates. Good. Looks great.